All right, thank you, Oliver. I guess I feel obligated now to explain the date, which is today's date. It feels still 2020 because it felt like 2020 was very long, right? Anyway, so today I'm gonna talk a little bit about how we can use fast radio bursts to study the evolution of gas in the universe. So I guess it's technically not related to the conference topic, but it is tracing the cosmic web and it is coming from galaxies. So just to start with credits, so I'm going to be presenting work that represents effort of many people. So from IPMU, we have several folks. There's Matti Natta, who was at the time at IPMU, now at Stockholm. Ilya and Yusin are still at IPMU. Sunil's in the audience, and we have Professor X from UCSC, as well as collaborators Nicolas from Chile and Jeff Cookie from Swinburne. So I'm going to be talking about results that are published in this paper up there. And also we work a lot with two collaborations, which is one is Craft, based mostly in Australia, and F4, which is a follow-up team based on that data set. So just a very quick overview of fast radio bursts. So this is a phenomenon that was first identified by Lorimer et al. In 2007. And the reason that it was discovered relatively recently is because in astronomy, we like to integrate for relatively long time, and by that definition, if you integrate for minutes or hours, any signal that's very fast will be integrated out. So this Lorimer went into archival data and discovered this phenomenon of like extremely fast, bursts that last like milliseconds. And so in any given frequency, this looks like a delta function in time. But if you look at it as a function of actual time, you see this sweep of frequency that I'll explain in a moment. But these are among the most energetic events in the universe. About of order 1,000 of such objects have been detected. And of those, I'd say this number is slightly out of date. About 50 have now been localized to actual host galaxies. And they are definitely extragalactic sources. It's unlikely they're within our own galaxy. So we don't know what these things are. They are most likely compact objects related to magnetar phenomenon. If you're trying to sell books, you might claim they might be ET solar sails. In fact, there's a whole website just listing all possible theories for fast radio bursts. But for the purpose of this talk today, we can more or less ignore their underlying nature, because we are concerned with the fact that the signal sweeps in frequency as a function of time, and that sound was the actual the sonification of that signal. And what you see here is actually due to the dispersion of the signal by intervening free electrons. So it's usually parametrized by something we call the dispersion measure. That's literally just the path integral over electrons. So if you're assuming that the origin of the signal is extragalactic, there's a few assumptions one can make. One is that virtually all the gas in the universe is ionized, apart from very small pockets of neutral hydrogen. Basically, to 10 to the, only about 10 to the, probably 10 to the minus 3 of atoms in the universe are neutral in some form. And also, of course, the good old astronomer approximation that everything is hydrogen and maybe a little bit of helium is also true. So to a very good approximation, if you're probing the free electrons in the universe, you're probing the baryons in the universe. So if you understand that fast radio bursts are extragalactic, you can start thinking about what might be the contributions of that integrated signal. So of course they are going to originate from something that we do not really know. It's probably within the galaxy, It's going to pass through the large-scale intergalactic medium. There's some probability it might pass through individual galactic halos. Eventually, it's going to get to the Milky Way and arrive at our radio telescopes. So the basic dichotomy that we usually think of is that the kind of, in terms of the extragalactic contribution, the basic dichotomy is that of the intergalactic medium on large scales versus the circumgalactic medium on round halo scales. So a couple of years ago, there was this beautiful paper by McCord et al. That analyzed the measures of a small sample of fast radio bursts that have been localized. In other words, after the discovery of the fast radio bursts, their position was isolated to an individual galaxy such that the redshift could be measured. And then this was plotted as a function of redshift. And you can see here, there's a solid curve here. That's the relationship you would expect if the omega baryon value from, for example, Big Bang nucleosynthesis was true. And so this result showed that the distribution of the dispersion measures as a function of redshift beautifully traced this relationship. So this was so-called, this solved the so-called missing baryon problem in the sense that, well, we now know that the baryons are out there in the intergalactic universe. But for any given sightline, there's at the fixed redshift, there is a large uncertainty in terms of the possible values that this dispersion measure could take. So a given sightline at a fixed redshift could pass through any number of halos or could be passing through a large-scale structure. So that still leaves open the question of how the baryons are distributed across the universe. So again, the assumptions here are that there is a diffuse IGM that we assume to be tracing large-scale structure. In other words, the cosmic web that follows lambda CDM. That should be some sort of CGM contribution in surrounding individual galaxies and groups and clusters. And so my assertion is that if you observe, the galaxies on both large and small scales in front of known FRBs, this offers a very powerful probe of the cosmic baryons. So this is an interesting question because most of us have worked with numerical simulations, either learning about them in talks or even manipulating them directly. But if you work with a dark matter only simulation, you'll find that at around redshift 0, about half of all the dark matter are within halos. And if once you have the N body, if you want to study where galaxies are, you might do something like say, okay, omega baryon is just going to be some fixed fraction of omega dark matter. And then that will lead you to assume that, okay, the baryons are going to be, that means that half of the baryons are going to live in halos as well, right? But recent results from hydrodynamic simulations completely disagree with this picture. For example, this is a beautiful figure from a paper by Iromlu et al. A few months ago. And the color scale here is the baryon fraction. And there's a 10 to the 13 halo, 10 to the 13 solar mass halo here with a circle of R200. And you can see that the fraction of baryons is actually very low within the sphere of influence of this halo. And it's actually all piled up outside of the halo. And the answer for why this is happening is because of feedback. So feedback is kicking baryons outside of galaxy halos. So of course, this is all in a simulation, but this is this leads to the intriguing question that okay, so if we could measure this fraction of halos, this fraction of baryons within and outside halos, one might be able to say something about galaxy feedback. So I'm collaborating with Daniele Sorini, who's these days in Durham. And he has been working with Romil Dave on a suite of simulations where the initial conditions are the same, but with different feedback prescriptions. So these figures are showing the fraction of the large-scale IGM versus the baryons within galaxy halos. And basically, depending on what the feedback prescriptions here, you can have very drastically different contributions inside and outside of halos. So this is something that we're hoping to study. So back to my observational assumption that, okay, studying foreground, the foreground galaxies in front of FRBs would be very powerful. So Sunil, in a paper a few years ago, basically did the first such attempt at this, where he studied the cosmic web and galaxies in front of one FRB. He had a fixed assumption for what the fraction of halos and what the fraction of baryons in and outside of halos were, but he showed that there's basically things kind of made sense at an order of magnitude way. So the next step is to actually have a statistical sample of such sightlines and constrain the fraction of the baryons in the IGM versus the CGM. So observationally, what might we want? So as I said earlier, there's this dichotomy between the large-scale contribution versus individual galaxy contributions. So this calls for a kind of wedding cake strategy, where in the central several arc minutes of the FRB, you want to go relatively deep with large telescopes to look for individual, possibly faint galaxies that might contribute to the dispersion measure. But on the other hand, to study the cosmic web, you need a relatively wide field survey with large numbers of galaxies to be able to map out the cosmic web. Of course, we're at the conference about the cosmic web, and we've heard beautiful results at all redshifts about the cosmic web. But certainly, at low redshifts, this calls for large numbers of spectroscopic galaxy samples. Of course, there's Sloan and other surveys. But most of the FRBs that we're looking at are in the southern hemisphere, where Sloan doesn't cover very much, and basically not many other spectroscopic surveys have mapped out the universe. So we've been running our own survey called FLIMFLAM on the Anglo-Australian telescope in Australia, which is a dedicated spectroscopic survey to survey foreground fields in front of fast radio bursts. So Yixin Huang is my student at U Tokyo, and I've basically dumped an entire redshift survey on this poor grad student, but she's taken it in good stead. So basically, for each FRB field, so this is a real data set from a well-known FRB, 180924, and this shows the beautiful cosmic web that we've mapped out in front of this field. So our goal is to reach around 20 FRB fields by the end of this year. So far, we have about 10 fields fully mapped out that we're analyzing right now. So with some of the preliminary data, Sunil has already used FLIMFLAM data to kind of look at an intriguing phenomenon, which is, again, this is the McCord relationship that shows the dispersion measure as a function of redshift. And the color scale here shows kind of the probability function for this dispersion measure given its redshift, given some fixed model. And you can so there's been an intriguing number of sightlines that seem to be statistically high from this relationship. So Sunil has been using FLIMFLAM and other large telescope data to try and analyze why some of these guys seem to be a bit high. I won't spoil his results here. Please go take a look at his poster. So given the large-scale galaxy field, if we want to paint on the amount of possible baryons in the IGM, we first have to do a density reconstruction. So for this, we've been working with code written by Metin Atta, which is called Argo. What this does is basically does a Hamiltonian Monte Carlo sampling of log normal density field that would be most consistent with the observed galaxies. So this is kind of a cartoon picture that shows a simulated density field, And given an ensemble of observed galaxies that traces that density field, we would be able to reconstruct the density to a pretty good fidelity. So given the large-scale cosmic web that we observe, and also individual faint galaxies that we might see, we are now able to build models given the amount of number of galaxies and the large-scale structure in front. So the basic model that we have is basically just a linear that the gas in the IGM is just a linear fraction of the overall matter density, and then basically an FW-like model for the individual halos. So the way to think about what the data set we have is that we have the FRB measurements. So we have n FRB measurements where we measure the dispersion measure, and we also have the foreground data in front of each FRB from which we can build models. So if you've learned linear equations in high school, this starts to look something like that, where you have a list of dispersion measures on the left, and on the right you have a set of the sum of the individual components. Of course, it's not just a linear relationship, but that gives you an idea for how we might want to study this. So Ilya Krikin is a postdoc at Kavli IPMU who has been working to build the likelihood analysis pipeline for this kind of data set. So basically, given the observed dispersion measures, we will compare with models and do a Monte Carlo analysis to make constraints on the IGM versus CGM baryons. So it's hard work. We're now analyzing the data, so unfortunately I do not have actual results to show you, but we do have pretty robust forecasts for what we should be able to achieve. So our basic science goal is to measure the relative distribution of the CGM and IGM baryons. So this is a basic forecast where for those three parameters where you have the FIGM and FCGM, and we also adopt the host contribution as a free parameter as well. So this forecast shows us that we should be able to place 10% constraints on those parameters with FLIMFLAM. And given future data sets, we should be able to do even better and make more detailed constraints on the CGM profiles. So as you may expect, going between 30 and 100 FRBs would go beyond 10% precisions into percent level precisions. But what if we just didn't bother collecting any foreground data and just looked at just FRBs on their own? And we'll see that if you didn't have the foreground data that we just assumed that we would have, the constraints dramatically blow up. So we did the exercise of asking, well, how much does the foreground data improve on our ability to constrain the FRB, to constrain the cosmic baryons? And we found that it would require of order a few thousand FRBs to place comparable constraints to what we would expect to achieve by the end of this year. And this is an assertion that has been confirmed by several other papers. And if you do not have localized FRBs, if you just have a bunch of FRBs where you cannot measure their redshifts, then you need another order of magnitude more FRBs to study cosmic baryons. So basically, for example, so Shirasaki et al. Found that you need a few tens of thousands of FRBs to place comparable constraints as what we expect to get at the end of this year. So I think I'm done. So basically, I was hoping, probably a year ago, I was hoping to have results to show by now, but it turns out that running your own large-scale galaxy redshift survey is hard and painful work. But I hope that I've given you a flavor for what we expect to be able to study. So by the end of this year, certainly we should. I'd hope to be able to report to you the basic early constraints on the IGM versus CGM baryon fractions. And I would like the theorists in this room, especially those thinking about galaxies, to think about how your favorite feedback models might affect the distribution of the baryons in the local universe. And I think, I guess the last statement I'll make is that there are new surveys coming on, especially CHIME is building outriggers in the northern hemisphere. And I think DSA is another project that's also going to identify large numbers of FRBs. And by certainly in the northern hemisphere, DESI is already doing what we've been suffering to do in the southern hemisphere. So we should certainly in the next few years have very good constraints on CGM and IGM. So thank you very much.
Thanks a lot, KG. Questions?
Very nice, KG. Can you explain how you actually combine the deep field sort of IFU or whatever 8-meter data with the wider field data and how that actually works in practice?
I think the short answer is that we don't really combine them in the sense that they're used to they're used to compute the models as separate terms. So given the deep data, we would, for the individual halo contributions, we would compute that second term. And then from the large scale cosmic graph data, we would assume that the baryons are just, a scale factor of the underlying density field.
So for every galaxy in the use field, there's a term for the DM halo corresponding to that.
That's right. Yeah.
Thank you for the talk. Do you have a sense of like how the baryon fractions you find with FRBs, how they compare to like other wavelength tracers, like UV absorption lines in quasar spectra, for example? Like how would there be significant differences that you find?
I think the beautiful thing about FRBs is that you only need to assume that the gas is ionized, whereas with most absorption tracers, you need to make assumptions about the ionizing background, the gas temperatures, the metallicities. So I think for most CGM absorption line measurements, there are serious assumptions and also modeling, right? Here, I think the modeling is literally just computing NFW profiles, whereas for absorption line tracers, it's much more involved than that. The other kind of, competing but not really competing method would be like X-ray measurements, which are basically tracing the hydrostatic profiles of galaxy clusters. But those, by definition, are generally probing galaxy clusters of masses of 10 to the 14, 10 to the 15. Maybe down to group masses, you can do stacking to try and look at their X-ray profiles. But certainly down to L star level, there is no comparable measurement. So I think there is, in terms of absorption line measurements, there is complementarity, but I would certainly argue that that the FRBs are less model dependent than most absorption line measurements.
Well, sorry if I missed this, but how do you model the Milky Way contribution to each line of sight? Is that a major contribution?
I did not explain this, but basically in practice, there is a population of halo pulsars, and you can also measure a dispersion measure from pulsars. So if like a bunch of pulsars in the Milky Way halo, basically people have built models for the Milky Way contribution based on that.
I guess how much uncertainty do you think there is in that kind of estimate, or?
So I think it's of order. So the is of order 10 or 15, maybe 15. I would say 15 to 20 of those units on the y-axis. Okay. So that's the uncertainty that subtraction brings to. Are those error bars? Those error bars include that, right? They include that, but also they include like error for the host. Okay, but the Milky Way contribution is subdominant for those error bars. Okay, but it's of order like maybe 20 on that y-axis.
So like maybe like 20 to 30% of the overall error comes from Milky Way uncertainty.
I would say less than that. Okay, yeah, at low redshift it would be significant, but at higher redshift it's small, but it's significant but not large.
Okay, thanks.
Okay, can take one more question. Maybe the next speaker can already start coming forward.
I just wanted to follow up on that for a second. My understanding is that there's been an attempt to estimate the electron abundance in the outer halo of the Milky Way using FRBs. So it's not something to ignore, it's something that's given an opportunity. Can you comment on, I don't know if you know about that work, but maybe you can comment upon what the future looks like to be able to do that separation and be able to learn more about the outer halo of the electron abundance in the Milky Way.
I think having foreground data is like Tabasco, well, not Tabasco, so Tapatio, like it makes everything better. So I mean, certainly I would say that having a sample with a localized sample with foreground data is certainly, I mean, it's just a matter of adding, more terms to the analysis and more free parameters. But certainly, it's something that one could imagine with time-out rigor plus DESI.
Yeah, well, it took me by surprise that there were these claims. I thought that was really interesting. So it's something that you could do.
Yeah. Thanks.
Okay, I think we have to, unless there's something very urgent we could take. Okay, let's take one more.
So the measurement that they have for the Milky Way halo is essentially they're getting it from 1 or 2 FRBs. So basically we just need a large population of low dispersion measure FRBs to get a more resolved map of the Milky Way halo contribution.